Now I invite Anuleka Pandey to formally introduce our resource person to our participant.
Thank you, sir. It is my pleasure to introduce our distinguished speaker, Mr. Ruben Samikannan. He is a seasoned professional with extensive experience in the field of information technology and services. He has held significant roles in various organizations contributing to advancements in technology and business processes. His expertise spans across the project management, software development, and IT consulting, showcasing a profound understanding of the industry's dynamics. Throughout his career, Mr. Samikanu has demonstrated a commitment to excellence and innovation, leading teams to success and implementing solutions that drive organizational growth. His leadership and strategic vision have been instrumental in navigating complex challenges and delivering impactful results. We are honored to have him with us today and share his insights and experiences. Welcome, sir.
Yeah, welcome. Thanks, Anulaka, and it was a nice introduction. So, shall I share my screen?
Sure, sir.
Wait a minute. Let me know.
Yes, sir, it is visible. Sir. The slides are visible, sir.
Okay. Fine. So can I see my full screen?
It is not in the slideshow format, sir. Sir, have you shared our entire screen, sir?
Wait, I'll share it again. Entire screen. Okay. Is it visible now?
Yes, sir, it is now in full screen mode, sir.
Okay. Okay, fine. So yeah, shall I start?
Yes, sir.
Okay. Yeah, today my topic is, and first of all, thanks to Mr. Padmanabhan and thanks to Mr. Pradeep as well for coordinating and bringing me here. So my topic today is renewable energy and power system studies, harnessing the future. So what I'm going to dwell in this topic is a high-level overview of the renewable energy and the power system studies. So yeah, I'm currently working as the senior electrical grid engineer for RW Renewables. So let me start off with the session. So I'll start off with the introduction to power systems. I believe you all would have gone through all these in the 5-day seminars or five days presentation. But just to recap, in power systems, as you all know, we have generation, transmission, distribution, and utilization. And in terms of generation, we all have this fossil fuels and renewable energy sources. And once they are generated, we use this transmission lines, either HVAC lines or HVDC lines, cables, AC cables, DC cables, and also in some places they go for the gas insulated lines as well, using SF6 or other mixed gases. So once the transmission of power is done from the generation through via the transmission, it gets into the distribution level, where the electricity is being used by the end users, such as ourselves, commercials, and industry customers. And then there will be some utilization as well, and for example, in industries and other places for lighting, HVAC, cooling purposes, etc. So, and then yeah, we have this power system planning and operation, where the utility companies, basically who are the network operators, do all these kind of high-level plannings. So they do from long-term planning, short-term planning, load forecasting till grid compliance studies. Long-term planning are like, planning the grid for the future. So they would foresee what might be the future loads that might be coming into the system for the next 10 years or so. For example, AirGrid in Ireland, who is the TSO, does this long-term planning. What they do is they assess the system for the next 10 years and see what's the load, what's the demand is going to be for the next 10 years, and then they do connect the generation onto the system to match the load. So basically, all these steps are driven based on generation and load matching. Yeah, they do this generation into they let this generation into the network to power the demand at the load centers. And also, they do this short-term planning. Short-term planning is the near term, where the economic dispatch, grid reliability is done to match the load, and also load forecasting. As I said previously, they forecast the load for the next 10 years. Some TSOs do it for 5 years. Some do beyond 10 years as well, and then project the and based on the load projection, they include the generation into the network. And finally, they do something called the grid compliance study. So whenever whenever there is a developer comes in and applies for a generation, either a wind farm or solar farm, or let it be a synchronous conventional generation. So the TSO would look at the applied generation capacity and do a grid compliance study to check whether the network at that node can handle that excess megawatts at that node. So based on that, that compliance study would be in relation it would be as per the grid code. So, and also the regulations which are available at that particular countries. And then to do all these, prior to getting the generation and the demand onto the network, they use this simulation softwares. So these simulation softwares can vary depending on various users. As we saw in the previous session, as I was listening on to Sharon's presentation as well, she touched upon the various EMT and RMS softwares. So it depends upon who uses the tools. So for instance, the utility companies mostly doesn't use the EMT tools. because as Sharon rightly said, it is mostly, locational specific. That is, you just analyze one particular region of the network, and you cannot have a full network, for example, if you want to model a full network of Ireland, you cannot have it in one single network in EMT network. But for that, you need the RMS tool, which is the PSSE, or in some instance, for UK, for example, use Dix Island Power Factory, but Ireland uses PSSE. So that's the difference. So for example, industrial distribution tools, you might have used tools like ETAP, SIME, SKM, NECPLAN, etc. So those are industrial specific. So they analyze just region specific network. So the remaining grid would be more or less a Thevenin source. So that's how the tools are basically designed for. But in terms of grid connected system tools, you have this systems called PSSE, Dix Island, etc., where you can have the entire country's network in one single software. So you can analyze the network with that software, and you can do anything with that. But mostly it would be RMS simulation. But Dix Island, to some extent, can provide EMT-based simulations. But to my knowledge, it is very difficult to do an EMT simulation for an entire network. So that's why it would be a time-consuming process, as Sharon rightly said. It would be a time-consuming process to do an EMT simulation for an entire network. The time step will be very small, so it would take infinite time to simulate EMT related studies. So that's why we have this EMT tools like PSCAD, EMTPRV, and ATP is kind of free software which you can download and use it. So what basically they would do is you can reduce your model from PSSE to a confined region where you want to simulate your network, and then leave the other parts of the network as a single Thevenin or a multiple Thevenin network. And then you can analyze your studies from there. For example, ABB, for instance, if they want to check their HVDC systems, if they are working fairly and correctly, they might, for instance, if they want to do an interaction study with another HVDC network or with another control system, they might reduce the PSSE network to a network which is suitable for PSCAD, and analyze that portion of the network where they connect the HVDC systems. And then they might be doing those studies and checking their control parameters, and then submitting those control parameters to the utility companies. The selection, as I said, selection criteria for power system tools, broadly depends on what you want to do. So if you want, if you're an industrial, if you want to do an industrial simulation, then it's best to go for ETAP or SIME or SKM like softwares. And if you want to do a grid compliance, then you need to have the entire network in place. Then you go for specific softwares like PSSE or Dix Island. And you want to see, the electromagnetic transients related stuff, then you have to go for electromagnetic tools like PSCAD. So the next question comes: why you need a power system simulation? Uh, First and foremost, as you all know, is hand simulations or hand calculations might be very difficult. For example, running a load flow. Yes, it can be done using hand simulations, but it's quite complicated. So that's why these kind of automated tools comes in and makes our work simplified, and it provides greater accuracy, and we can do optimizations as well very easily. Just change whatever we want inside a generator, or delete a line, or maybe change the rating of the line, summer rating or winter rating of the line, and see how it behaves. Change the transformer rating and see how the transformer of this, or how that transformer behaves, something like that. And then also it eliminates the risk, the potential risks of errors can be eliminated using the simulation tools. So this is just reflects what I said previously. So this just gives tools which are used by different sectors. So the transmission and distribution operators usually go for the RMS tools, which is ESSE or the Dick Silent Power Factory. And then the industrial users go for the for ETAP related tools, just for power quality, reliability, fault protection, and then maybe control and traction kind of studies. And then renewable generators do use some, they hire consultants to do their own studies. And then they have to adhere to the grid code and other regulatory considerations as well. So power system simulation techniques. Yeah, this again reflects what I said previously. There are RMS and EMT simulators. So RMS simulations can perform load flow, transient stability, and voltage control. So it depends mostly on the phasor-based methods, as Sharon, detailed in her presentation as well. EMT simulations are focus on high frequencies, like like 10 to the power 5 or microseconds or nanoseconds regime. So these tools look into transients which are of high frequencies. For example, if you want to do a lightning study, you might have to go for PSCAD or EMTPRV, or you want to do a very fast transient over voltages, for instance, which is in nanosecond regime. You might again go to the PSCAD or EMTPRV, as RMS cannot capture that faster frequency range, higher frequency ranges. That's on that. Selecting the right power system tools. I think this has been broadly covered in the previous slides. Steady state and dynamic studies. You can do both in the tools. Power flow. You can do power flow analysis. You can do optimal power flow as well. Optimal power flow, including, you can include contingencies, n-1s, n-1 -1s, or you can do, or even you can do entire hour of the year run. For example, you can run 8,736 hours of simulation in tools like PSSE. So it gives the load flow for every hour of the network, and also it varies the generation and load based upon it varies the generation based on the load as well, and you can see how the system is evolving for the entire hour or so here. And you can include contingencies as well. For instance, you can model n-1 and n-1 contingencies as well on those on top of that on top of the optimal power flow simulations, and you can do short circuit analysis. Um, and again, these can be done for the entire hour of the year, but it's quite complicated. But it is doable when you can have the sequence files, the sequence files like zero sequence and positive sequence, because it's very difficult to get or model the sequence data for every hour of the year. So that's where the short circuit analysis gets complicated, and we do short circuit analysis only for one time domain, just for one instant. And transient stability, I think this can also be done for the entire year of the entire hour of the year. You just have to have the dynamic models in place. For instance, in PSSE, you have to have the DYR file. So the dynamic files have to be included for the generators, so that for one particular disturbance, how it would react, it would be captured only by the dynamic file, which would be provided by the generator vendor or the supplier. And these are all the equipment modeling in PSSE, which is available. For instance, generators, transformers, FACTS devices, loads, and branches. So these are all the simple equipment which is available just to model the entire country's network. Yeah, renewable energy integration challenges. This is another challenge because, as you know, renewable energy is quite intermittent. So, including a wind farm to an existing grid would be a greater challenge. And so what utility companies does is take the dynamic response of the wind farm and then connect and then plug it to their grid, and then perform some dynamic studies and other studies to check how the frequency, the voltage, and other parameters are panning out. And they do this along in relation with the grid code and other regulatory other regulatory requirements as well. Yeah, this is again renewable integration studies. Just they do the compliance studies, installation coordination studies. They might be coming at the last phase. This might be done at during the design phase. But when you're going to connect your generator in, you might have to do first the grid compliance studies and the renewable energy modeling, and then the reinforcements and expansions needed for that. Yeah, at present, in power system planning, for instance, in AirGrid, who is the TSO for Ireland, uses a lot of automation and a lot of scripting. I have worked with AirGrid as well for a short stint, and what they do is they have all these Python scripts in place, and then they just run those Python scripts along with those inside those PSSE tools, and then they link with the Plexos outputs. I don't know how many of you are familiar with Plexos, but these Plexos gives gives the market models as the input to PSSE for running those optimal load flow simulations for the 8,736 hours in a year. So what would this Python script would do is combine the output of the plexos and integrate them with PSSE, and then it automatically, when you call a script, it would automatically run for the 8,736 hours, and then it gives you the optimal power flow for the entire hour of the year. So basically, what I'm trying to say is automation is the way to go. Automation is the future for these tools. So, the upcoming tools have this artificial intelligence as well. They are progressing through this route. But at present, it's the Python scripts which are of use at this stage. But I believe ETAP is doing some artificial intelligence to incorporate into their model as well, where you can just inform the tool to do some analysis for you. I believe the progression or the future is going to be towards the automation and the artificial intelligence. So yeah, that's about the power system simulation tools. So it plays a crucial role in the integration of the renewable energy sources. So if we can, have a good grab of these tools and good knowledge of these tools, and along with Plexus and artificial intelligence automation techniques, we can play around with a lot of things in these tools, and it would make our lives easier as well. And then just to give an overview of how the power system network in Ireland looks like. I know most of them would be familiar of the Indian network, but I thought of giving an overview of how the system in Ireland looks like, and what they do in Ireland, and how it is set up in Ireland. So just a change for you guys from the usual topics. So this is the Irish network, power system network in Ireland. So this is the portion which is in light yellow is the Republic of Ireland, and the portion which is in darker yellow is the Northern Ireland, which is part of UK. So it's quite complicated seeing the setup, but the power system network is quite simpler. So both the Northern Ireland and the Republic of Ireland are interconnected using a HVAC line, which is a 400 kV line, and also a 110 kV line here. So these work synchronously to each other, although the voltage levels are quite different. The voltage levels in the Republic of Ireland goes up to only 400 kV. Compared to India, we have the 765 kV levels, and maybe exploring beyond that, because I'm not updated as I'm not working with Indian grids anymore. So it's been 5 years now. So yeah, just coming back to this network, they doesn't have HVDC lines as well. So it's all it is all HVAC lines. So this red line is the only 400 kV line, which runs from the southwest all the way to its state's capital. And the green lines are 220 kV lines, and the black lines are 110 kV 110 kV lines. So those are the three voltage levels in the Republic of Ireland. And if you see in Northern Ireland, there are only two. There are three. Sorry for the mistake. It is just two. One is the 110 kV line, and one is the 275 kV lines. So that's how it is. And the system operators, as you can see, are AirGrid and Sony. So AirGrid is a system operator for the Republic of Ireland, and Sony is for Northern Ireland. So that's on the Irish network. So now, how they operate is important to know. So they have this transmission and distribution system operators in Ireland. So the transmission system, as I said, is 400, 220, 110, and 275 in Northern Ireland. So the transmission system is governed and operated by AirGrid, and there are two HVDC interconnectors, but they are not HVDC networks inside the country, but they are two HVDC interconnectors to other countries, which is called the EVIC, which is the East-West interconnector, which is the interconnector to Great Britain, UK, and there is a Moyle interconnector as well, which is an interconnector which runs from Northern Ireland to UK as well. And there is a planned interconnector called Celtic. This would also be an HVDC VSC line, which would interconnect the Republic of Ireland with France as well. There is another Celtic interconnector 2 as well, which is planned beyond 2027. So that will also be an important step in the transmission system in Ireland. Distribution system is 38 kV, 20 kV, 10 kV, and 400 watt to 30 kV volts in Ireland. And the distribution operator in Ireland is called ESP Networks, and in Northern Ireland it would be NIEN, and they operate with an SNSP level, which should not be above 75%. So what it does is, this is a formula to calculate the SNSP. So whenever there is an increase in SNSP level, the transmission system operator or the DSO would issue a curtailment to the generators. It might be either wind farm or the solar generators, or it might be the conventional generators as well. So yeah, I've explained about the voltage level, the interconnections. They don't have any direct connection with the mainland Europe. That is, mainland Europe is Germany and surrounding countries, but they just have interconnections with the GB, with UK and France. AirGrid has, AirGrid, who is the TSO, has this, smart grid dashboard, so call it, where you can, go and see what's the demand, what's the generation, and what's the SNSP levels are. I'll just quickly show you how it works. So before that, I just want to know, are you guys okay with, uh, you know, gaining some knowledge about Ireland system and how European system works? Can I get an answer? Maybe put an S in chat or great. Perfect. Okay. So yeah, I'll just go about how AirGrid or the TSO of Ireland usually, tracks all the data. So if you go to AirGrid, if you type AirGrid and go to their homepage, and if you go to the grid uh, and then go to real-time system information, and then you can see all the system demand there and all the fuel mix. So if you can see, renewable energy is contributing 23% of the total energy. So the net import, this is the import from the interconnectors from UK and from UK for now. So the wind generation is here. So it'll be a very nice dashboard which they use to track all these. So yeah, this you can see the overview of how it is. So you can see the system demand there and how much wind generation is there. So at present it is standing at 204 megawatts and 5.7 gigawatts of demand. So and you can click each tab here. So it shows how much demand uh, at present now, and then how much demand, how much would be the forecast for today, and then this is the overall demand as well. So you can see this for all the days. So if you can click this, it shows how much it was yesterday. So it's quite handy to have that. And then this is the generation here. So you'll have this. This is the total generation, and then at present, and then you have this thermal generation. What's the percentage of thermal renewables and the net import. So at present it is mostly import. So mostly Ireland imports power from UK because the power is cheaper in the UK compared to Ireland. So that's why it is always importing at this stage. So that's about generation. So you can see the actual generation here. And you can also forecast or see the latest wind generation there. So at present it is generating 204 megawatts only, but it has a capacity of 4.6 gigawatts in the system. So this is the interconnector, which is you can see here EVIC GreenLink. Yeah, GreenLink is also an interconnector which runs from, I think it's from the Republic to GB as well. Yeah. See here, from Ireland to Wales, it is EVIC and Greenland, and from Ireland and Scotland, it's the Moyle interconnector. So, and you can track the frequency as well, at what frequency the system works with. So similar to India, it is a 50 megawatt 50 hertz system, yeah, it's in the range, so it has to operate in this range as well. So as I said before, this is the SNSP range within which the system has to operate. So the non-synchronous this depends on the non-synchronous penetration. So if the wind or if the solar penetration is too high, then this SNSP percentage would be would be more. So it should not, if you can click here, if you can see that the percentage. So this has to be maintained less than 75%, meaning that your wind and solar or the renewable energy penetration should be a little less. If not, if it exceeds 75%, then the grid operator issues a curtailment to the wind farm or the solar farm to reduce the generation a bit. And they are working for demand side response as well. So it is coming in the future future planning, which is done in Ireland. So what it would do is it would signal a reduction in the demand as well. So if some developers are okay to, if some developer or demand center or a data center are ready to reduce their demand a little bit, then that also helps to manage this as an SP and in turn the grid stability as well. So that's on that. And regarding the maps, sorry, and regarding the Irish maps and how they develop the network for the next 10 years, you can see them through. Again, you can go to EirGrid's website. Who's TSO here, and then go to publications, and then go to their transmission and go to the forecast system. So this document is the document which forecasts the network for the next 10 years and how is the system going to look like for the next 10 years in terms of generation, demand, and also in terms of system transmission line reinforcements, reactive power compensation, so on and so forth. So I think I've already opened. Here you go. So if you read through this document, this is a very good document to go through to understand the power system of Ireland and what is planned for the next 10 years and what generation, what sort of demand and what sort of reinforcements are going to happen in the network. So yeah, kind of slow, yeah. Sorry, it's kind of slow. Maybe we'll go through, but that's the document which is available in a good site. Can have a look at it maybe later. And then yeah, we'll talk about what's the renewable energy and its environmental impact, and in the further slides we will see what sort of renewable energy sources are being used in Ireland and how they generate the power, and we'll see some a project in Ireland as well, which is a co-located wind farm plus BESS project. So we'll go through this one by one. So as you all know, these are the renewable energy sources which are available globally. So you have the solar, wind, hydropower, biomass, geothermal, tidal, and wave energy. So the intention of putting in the renewables into the network is the very intention is to reduce the carbon dioxide emission, as you all know. So as all countries have, Ireland do have this kind of renewable energy target where you have to reduce your carbon emission by some percent, by some percentage. So we'll see what's those in a later slide. But as far as Ireland is concerned, the major renewable energy sources are solar and wind, um, and there is another um, technology as well, which is called the BESS, which is called the battery energy storage system. But the battery energy storage are used in order to support the solar and wind and other renewable energy, but they do not generate power, as you all know. And there is another power technology as well, which is called the airborne wind technology. I didn't add it here because it is in initial stages in Ireland. But yeah, it is an interesting technology where there is like a kite. There is like a kite which they send to this. They will send a kite with a rope inside it, with a rope attached to turbine in the ground station. And what this kite does is it rotates like in like a shape of 8 in the air. So with that, with the motion of that kite, the renewable, the power is produced and it is transferred from the ground station turbine into the nearest grid as well. So that's in the initial stage at the moment. So just letting you know for information. So the major technologies in Ireland in terms of renewable energy is wind energy, BESS, and solar. So at present, by the end of 2022, Ireland has an installed wind capacity of almost 4.7 megawatts. So it is contributing to nearly a third of country's electricity generation in 2024, sorry. So in Ireland, there is enormous availability of wind. So if you get to visit Ireland, maybe you will see the wind is blowing at all times of the year, particularly in winters. It is too high. So, and solar energy is not much available in Ireland. As you know, the European countries all don't have much sun in their zone. It's not like India where you get sun all throughout the year. So in winters you don't see sun most of the time, but it does produce some amount of power. Nowadays, the technology for solar is much more that it captures even very small amount of sunlight and then produces power. And yeah, there are technologies as well which focuses on solar energy from space as well. So I think one, two, but it's not available in Ireland yet. But there are working groups in Ireland which are looking at Ireland and elsewhere, which are looking at generating solar energy from space that is get the sunlight reflected from the sun from the space and then reflect back to Earth and then generate the solar power from the ground station there. So that's ongoing in terms of solar, but in Ireland by 2024 it's 1 gigawatt of solar energy generation, and yeah, and the next technology is battery energy storage systems. So so these would be the potential leaders going forward to support these two technologies like wind and solar, to provide all the ancillary services, for maintaining the frequency. Because if you don't have your synchronous generation, you don't have your you can't control your frequency. So in order to, if the network is fully going towards solar and wind, so you will not have your synchronous generation to control your frequency. So that's where BESS comes into picture, to charge and discharge the megawatts into the system to maintain the frequencies. And also it can provide synthetic inertia as well, which some of the utility companies and other countries are looking to explore. But at present, Ireland doesn't look at synthetic inertia yet. But they are looking at just for frequency control. And they do have future targets as well for 2030, as most of the European countries and other countries apart from Europe has. So it has an ambitious target of 9 gigawatts of onshore by 2030, and 8 gigawatts of solar as well, and at least 5 gigawatts of offshore wind capacity. I don't know if anyone has covered offshore wind yet, but we'll see in the later slides how offshore is being planned for 2030 and beyond as well. But as far as 2030 plans are concerned, Ireland has this strict target of reaching this, and there is this climate action plan which Ireland government publishes yearly, so that the TSOs has to, or the grid operator has to adhere to. So based on that climate action plan, this is the target for Ireland. So yeah, this is a renewable energy development in Ireland. So what happens is, so you have these grid connection companies called the TSOs and the DSOs, through which the developers has to submit an application for connecting your wind or solar farm, and then you have this application process and everything to look at the network and assess how the network would behave while accommodating your wind or solar farm. So that's done by the grid operator, and in parallel you have this planning process as well, and you have this PPA, power purchase agreements with your grid operator as well. So if you want to put your wind farm at a particular node, it's not just like that you can put a wind farm there. It has to go through a planning process, which is called the development planning process, to get permission from the nearest what do you call it, like a municipality in India. There is a county council in Ireland where they should attain this permission to putting the wind farm, and from that wind farm to connect to the grid. So once they get that approval only, then they can go in for the application for the grid. So the challenges would be mostly the grid. So if you put a wind farm, there might be no grid growth in that region where you put your wind farm or solar farm. So you need to be sure before you put your wind farm that there is grid available at that location. For instance, Ireland in northwest, the grid is not much evolved in that region. So putting in your wind farm or solar farm doesn't make sense because you can't you can't transfer your generated power to the load centers where you want to. So in that case, you might have to negotiate, or you might have to have initial screening or initial discussions with your grid operator in order to how to develop that grid in order to put your generation there to take your generation to the load centers. So yeah, all these processes has to be done to attain this the climate action target of 80% of renewable electricity by 2030. So that's the ambitious target for Ireland to attain 80% 80% of electricity has to come from renewable energy source by 2030. So all the utility companies, like all the TSO are working towards it, and we'll see what's the plans beyond 2030. I don't know how many of you are aware what's the plans for many countries beyond 2030, but beyond 2030 it has to be net zero, no renewable or no fossil fuels or no carbon emission should be from any of the sources of from any of the sources into the electricity network or into the atmosphere. So these are the top renewable developers, or the wind farm, solar farm developers at present in Ireland. So you have RWE, Statkraft, RES, Midsea, Mainstream, Ørsted, and SSE Renewables. So this is one of the co-located wind farm plus BESS project in Ireland. So you can see that, so it's called co-located wind solar because the wind farm is co-located with the BESS. So, so you can see there's the wind farms nearby, and I mean this is not the actual project site. This is I just downloaded it from one of the project, but this is how a co-located wind farm plus BESS project looks like. So so you can see here the containers are the BESS containers, and the small white containers are your inverters. So I think a 10 megawatt of BESS has two containers similar to this. So if it is, and of this project is a 80 megawatt of BESS, 80 megawatt of wind farm and the 60 megawatt of BESS. So this has to be at least 12 to 15 containers. So this has to be 10 to 15 containers to accommodate the 60 megawatt, and it should have its own inverters as well. And these are the wind farms. So for this project, one wind turbine will generate 4.8 megawatt of power. So if it is 85 megawatt, it has to have 17 wind turbines similar to this at a spread out in all spread out locations. Similar to this, there are a lot of spread out wind farms there. So it's a Nordex 4.8 megawatts wind turbines, which are 17 numbers. So there is this regulation in Ireland where, if you are more than 50 megawatts of generation, you have to go to the 110 kV level, and if it is less than 60 megawatts of generation, you have to go into connecting to the MV side, which is 38 kV side. And then, if it is less than 40 megawatts, then you can again go to a 38 or up to 38 to 10 kV network. So at present, most of the developers don't go beyond below 10 kV because that's very low, and they won't get enough revenue if they generate very less um power. So that's how it is. This how the wind farm and BESS would work together is, it would have, maybe I can show you the layout of a collocated wind farm BESS project. Just bear with me. Connection is quite slow. Yeah. So this is the layout of wind farm and BESS project. So you can see the wind farms would be spread out in this location. And then you can see here, this is the blue line which comes from the wind farm and then goes into the control building there. So, and your BESS would be here. You can see all the containers and the inverters and its corresponding inverters there. And this is the switch yard, and this is the grid here. This is the grid. This is a loop in loop out connection, which is like loop in loop out connection means your project will be connecting to this overhead line. So yeah, that's how it is. You just tap power from this, and you connect to this overhead line just by power tapping, and then they will remove this. Going forward, they will remove this section, and so it would be connected like this. This side will go. This side of the network goes this way, and this goes this way, and this will be eliminated from the network. And this is the switch yard, which consists of all the circuit breakers, CTs, VTs, transformers, surge arresters, etc. So in this drawing, you have two transformers, one for BESS and one for the wind farm. But we are discussing to have a single transformer to accommodate both the BESS and the wind farm. So it will have a one common coupling here for the BESS and the wind farm. So that's how it is. So how it works is, the wind farm would be producing power, and it will be sending it through these bay into the network using these lines. And then the BESS would be idle for most of the time, but whenever there is difference in frequency in the network, the grid would give a signal to this BESS, and then this BESS would either charge or discharge based upon the under frequency or lower frequency in the network. So that's about that. I think there is an SLD as well, which I can show. Sorry, this one. So this is the SLD of that layout. So as you can see, this is that single transformer which I was talking about. So this is the line. This is the network which goes to the wind farms here. So these are all goes towards the wind farm, and this is the BESS. So both the BESS and the wind farm are co-located at a common coupling here, and then goes into this transformer, which steps up the voltage to 110 kV. And by the way, this the line which I showed you here is a 110 kV net line. So this transformer steps up the voltage to 110 kV, and then the switch gears also are also rated at 110, and then it is delivered to the destination. And these are the two lines which I showed you there. One goes to one station, the other goes to Nokra, and one goes to Woodhouse, and then yeah, that's how it is. And you need a two future bay as requested by the grid operator as well. So that's on the SLD. And then, yeah, you have all these planning and grid process, as I explained you previously. You should go through the planning process to get approval from your local county council, and then once you get your planning consent, and then only you need to go and apply for the grid. So in terms of grid, you have the design phase stage, procurement stage, and construction stage. Sorry, I'll get some water now. Just give me 2 minutes. Sorry about that. Yeah, we'll see what's beyond 2030. I don't know how many of you are beyond familiar with what's going to be beyond 2030. So as far as Europe is concerned, I don't know what's been planned in India at the moment, but in Europe, this is the plan. So by 2030, it plans for 100 gigawatts of offshore wind. This I'm just explaining in terms of offshore, because 2030 and beyond, it's going to be full offshore. So your seas and your oceans are going to be bedded with a lot of HVDC cables. Is the future. So because your onshore will be full of the network will be full. So the next available network which is available is the oceans. So we are going to explore the oceans as well, with all the connectivities and all the infrastructures in the oceans. So 2040 is they're planning for 100 gigawatts of offshore wind across Europe, and then they are planning for they'll be expanding the offshore infrastructure, as I said, and there will be connections within the connectivities within the countries inside oceans, and then by 2050 you'll be having offshore grid similar to onshore grid which you have now, and the offshore and the onshore grid will be integrated with each other. So yeah, this is, I mean, I'll explain what's ENZOE. ENZOE is nothing but it coordinates all the TSOs which are available in the entire Europe. So it involves Ireland, Iceland, UK, Germany, Sweden, up until Ukraine. I think I don't know if Ukraine is included, but there were some talks that Ukraine is also included. But at that time there were some wars between Russia and Ukraine. But I don't know what's the status now. But yeah, if you see, these are the countries. There are 39 TSOs from 35 European countries. All are coordinated by this ENZOE. So ENZOE's version is aims to get an integrated network for the entire Europe, and then integrate the offshore and the onshore as well. So how this has to be done? So is a question now. So you can't just go ahead and do in the real time. So similar to onshore, you have offshore studies because you need to build your offshore network from scratch. So you need to have this Plexos models um, in place. Just give me a second. So, yeah. So what happens is all these TSOs will be having their own Plexos models, which would be having all onshore models at this stage. What they will be doing is they will be incorporating their offshore network as well into this Plexos models, and then they would be uh, giving those Plexos models to INSOE, and then they will be performing some analysis and detailed studies in terms of Plexos first, and analyze what's the most cost effective way to do, because Plexos gives output in terms of cost, because cost is the first um, um, first criteria to fulfill. So once cost is determined, and then you do the grid related studies in tools like PSSE, Dixisland, PSCAD, etc. So yeah, once that is done, so let me show you uh, the offshore development plan. So this is the offshore development plan, which ENSO is coordinating at this stage. So they have split the oceans into different sea basins. You can see here. So there are five different sea basins. So one is North Sea, one is Baltic, one is Atlantic, one is Mediterranean, and the other is the Black Sea. So part of North Sea is Belgium, Denmark, France. I think I don't know what is DE, but Ireland, Lithuania, Netherlands, Sweden. So Ireland comes under the North Sea region. As you see, this North Sea waters is part of Ireland, so they come under North Seas. And Ireland is also part of this Atlantic because their sea covers the Atlantic as well. So if you can see, they will be part of the Atlantic as well here. So that's how the sea basin is split across. So each countries have given the responsibility to plan their offshore network, but they have strict targets as well. For example, this is the non-binding agreements for each of the countries. So if you see, this is the Northern Sea for Ireland. Just bear with me. Yeah, there you go. So this is the non-binding agreement for Ireland. So for Ireland, by 2030, they might have to do 4.5. In fact, it should be 5 megawatts, 5 gigawatts, sorry. And by 2040, it should be up to 8 megawatts. And by 2050, they should do up to 17 gigawatts, sorry, 20 gigawatts and 13. Sorry, I was saying France there. So these are the non-binding agreements for all the member states, they call it, that is each countries, and and in total, Ireland has a net target of 37 gigawatts till 2050, because this is only the Northern Sea basin. And if you see, is it, uh, if you see the Atlantic, because Ireland is part of the Atlantic as well. So if you see the Atlantic Sea basin, so it is 15 gigawatts here. So 15 plus 20, it is 35 gigawatts, which is which is a goal for Ireland by 2050. So, as I said previously, sorry, as I said previously, offshore is the way to go beyond 2030. So up until 2050, at least in Europe, offshore grid would be formed. There might be interconnections between various countries in the seas. So there might be wind farms in the oceans as well, which is called the floating offshore, or standby or standalone offshore. They call it offshore wind. And then um, these offshore wind would have interconnections as well. Um, for instance, you have interconnections with Denmark and the nearby country. I think it's Denmark and Norway, which has offshore network which is connected in the sea as well, which is called a hybrid interconnector. So that's the future of offshore, and the offshore would be interconnected with the onshore going forward. And then you might have all heard green hydrogen, which is the future uh, uh, future way to go. So all countries, including Ireland, is progressing towards that. So there are some initial work done in Ireland to produce green hydrogen. So as some of them might not know, green hydrogen is the hydrogen which is generated from the excess renewable electricity. For instance, if all your demand is met, and if there is excess renewables, then you can export the excess renewables into electrolysis process, and you can generate your hydrogen on site or even at some other locations as well. So, yeah, as I said, it is produced by electrolysis, which splits, in which the renewable electricity splits the hydrogen and oxygen uh, uh, apart, and then hydrogen is stored as compressed gas or liquid, or even converted into ammonia or methanol for easier transportation. So going forward, the conventional thermal plants might be converted into hydrogen plants. Maybe the hydrogen gas might be um, used as a source to run your turbines, uh, and also there might be, the gas pipelines within the country. Um, for instance, in Ireland, they have this similar to ENSO-E. They have this ENSO-G, and they have this Gas Networks Ireland as well, which transports gas across entire the entire network. I mean, entire Ireland, um, because we use cylinders in India for usage, but in Ireland it's like gas pipes all over the country. So going forward, that gas would be converted or replaced by hydrogen gas, So, so the grid operators and the government is going or leaning towards that plan, and also there are plans to um, construct gas pipelines within the countries as well along the oceans as part of um, the 2050 plan. So uh, so yeah, that's about it. And the challenges would be the cost, as so that's why they're doing the Plexus modeling now. So how feasible and how cheap or how economical we can build these pipelines, and we can build these uh, networks in the oceans and integrate it with the onshore, is what they're seeing at this stage. And then yeah, the hydrogen pipelines, the existing gas pipelines has to be replaced by hydrogen pipelines, which could be expensive. Storage, storing, you need you need facility to store hydrogen, so you need facility for that. And then um, the losses, efficiency losses as well, which has to be taken into account. Um, and then yeah, that's about it on hydrogen. Um, so some of the developers have already started developing hydrogen onshore as well. So how it works is, like, they have a wind or solar farm connected to the grid. So whenever their wind or solar farm produces excess electricity which is not required by the grid, they use it on site for electrolysis and generate their own hydrogen and store it for later use. So yeah, that's how it works in Ireland at the moment. So yeah, that's about it from my side. If there is any questions, happy to take. I click the MS Teams.
The session is now open to participants. Participants can ask questions if they have. If there is no questions, we will wind up the session. So if any participants have any questions, they can put the question in chat box, or they can unmute and ask. Since there are no questions, shall we wind up the session, sir?
Yeah, can wind up the session. Yes.
Thank you, sir. Thank you for the very detailed and in-depth session.
No
We are
problem.
grateful. You
No
have
worries.
sacrificed your weekend for us.
Yeah,
You may be having several
that's
plans, but
that's the tough part. Yeah.
yeah, sir. Sure. Thank you so much for that, sir.
Thank
Now
you
I
so much.
invite.
Thank you so much for you as well. Whenever I reach out with any questions, you are answering then and there. So thanks, Padmanabhan, and thanks to Pradeep as well. I don't know whether he's here, so thanks to him as well. And yeah, thanks to everyone for listening in. And thanks for the opportunity as well. Yeah.
Thank you,
Thank
Ruben
you,
sir.
sir.
Thank you for gracing this. We have learned a lot of new things from you. When we have planned I want to cover every aspect of this IBR power systems. So we meticulously planned the session titles, but we forgot to plan the planning into the session. Really cover the planning as systems to this point of view, and we have showed the extensive list of the documents to us. It's very insightful to us, and you bring us in front of how our will be, and we have learned a lot of things from you, sir. Thank you so much for coming, sir.
No, no problem. Thanks for this.
Yeah.
Hope it is useful. Yeah.
Very useful, sir.
Thank you.
Now I invite Arudra to deliver the vote of thanks.
Thank you, sir. Good evening, everyone. It is with immense gratitude that I take this opportunity to thank our distinguished speaker, Mr. Reuben, for his insightful session on renewable energy and system studies. His expertise in grid management and renewable energy integration has truly broadened our knowledge and inspired us to explore innovative solutions for a sustainable future. Sir, your session was highly informative and thought-provoking, shedding light on the latest advancements and challenges in renewable energy. We sincerely appreciate your time and effort in sharing your valuable experience and guiding us towards a greener tomorrow. On behalf of everyone here, I extend our heartfelt thanks to you, sir. I take this opportunity to express my heartfelt thanks to all those made this faculty development program a great success. I would like to extend my gratitude to the organizing committee, coordinators, technical team, and faculty members who have put in tremendous effort in planning and executing this FDP successfully. From handling the visual audio setup, network connectivity, and presentation logistics, your hard work, dedication, teamwork, and attention to detail has played a crucial role in making this session seamless and effective. Finally, I thank all the participants for your active involvement and enthusiasm. Your engagement and thought-provoking questions have made this session even more interactive and insightful. Once again, thank you all for your contributions and support in making this event a grand success. Thank you.
Thanks, madam.
Thank you, Arudra.
So shall I drop off then?
Sure, sir. Thank you, sir.
Thank you so
for
much.
the
Thanks
session,
all.
sir.
Bye-bye. Have a
Yes,
good
sir.
evening.
Thank you, sir.
Bye-bye.
Thank you, sir. Bye.
Bye.